ChipWhisperer is my entry to the Hackaday prize. So this deals with security in embedded systems, and you see this all the time, whether it's uploading firmware to a router, whether it's entering some sort of license code, locking or unlocking your card. There's security everywhere, and if you're an embedded hardware designer, you might know this even more because you've done stuff like used AES bootloaders or put encryption on your system to protect your IP. The problem is, even if the encryption is done correctly, there's ways to break it. This has been known for a long time through differential power analysis published in '98. And since then, there's been a number of papers demonstrating these attacks against real products. And it's not just differential power analysis, there's other issues like you can do glitching where you cause the code to execute incorrectly. So your authentication code might just skip a check that it should have done. And you can show this, for example, here I have a regular Android smartphone, and I can cause it by inserting a glitch into the system to calculate a result incorrectly. And since this has been known for so long, there is commercial tools that will help you deal with this, but they're just too expensive for small companies. So into the mix, I'm throwing ChipWhisperer. This is a totally open source project. And it looks something like this in the commercial realization. You have a little fancy box that does your power measurements and has lights to indicate what's going on. There is a board that you can learn about. You can also target your own board. And then there's also all sorts of probes that you might need and breakout boards. So everything you sort of need for a full system. And inside that metal box is, so there's the board on the left I showed before, and inside that metal box is this FPGA based baseboard. So there's a Spartan 6 LX25 board with high-speed USB, high-speed ADC with variable gain amplifier. Underneath that there's power supplies, and there's a USB AVR for programming. And on the back side there's my fancy silkscreen. So that's just part of this project, is the hardware. The hardware interfaces to a open source software platform, and the software can actually talk to other devices and other oscilloscopes and everything. And open source doesn't just mean, that the source code is open, that the FPGA code is open, and the PCB designs are open and everything. It also means that there's a full documentation. There's a wiki page, for example, that tells you how to build the devices, not only instructions on how to build it, but a bill of materials and even a parts list you can copy and paste right into DigiKey to make this even easier for you. And to round it out, there's a full documentation on everything from how to install the software itself to a whole bunch of tutorials. Right now I think there's 6 or 7, and the tutorials show you, for example, how to actually perform the AES, break the AES system. And you don't even need the hardware to do this because you can download captures I've done. And in addition, there's a discussion forum to talk about that if you have issues. So what's involved in the project from an engineering perspective? So we have two sides to this. We have a software side and a hardware side. The hardware side has a whole bunch of FPGA blocks, including stuff like a analog pattern matcher to trigger in real time on patterns in the power measurements. And you can actually disable some of these. So if you need to fit in a smaller FPGA, you can turn off some of these blocks. And here's an example of a smaller FPGA it fits in, a Spartan 6 LX9. From the software side, it's again designed to be very modular, and half the software is used for capturing measurements, half the software for analysis. But you can, in fact, just capture the measurements and then export everything to MATLAB. The open source nature makes this very easy. So here's the software. The software is written in Python, using PySide as a GUI, and it's a fairly complex project, but everything, you can rip out some of the modules for use in other purposes, like using them just to drive a scope normally. So when you start the main window, it looks something like this. And for example, there's these script setups that'll run a whole bunch of different demos. So if I have the hardware, connects to the hardware, does a measurement, and I can view that it's doing the encryption right. You can do stuff like control the FPGA to generate specific frequencies to drive to the system. And once it's all set up, you just hit a button, it captures the power measurements. You load this into the analyzer. In the analyzer, you can do additional work, like if you need to filter it. And finally run the attack. So in this case, what we'll see is that the correct encryption key will appear in red and very quickly filter to the top. So this is showing you how the ChipWhisperer can be used to really quickly evaluate your systems for embedded security and how your implementation has performed.